Hey then everyone, good morning once again. So the reason I'm here is I'm afraid Stephen's got delayed coming in on his train. So I'm going to give the maths fundamentals lecture now, what you normally have at 11. And I think you'll probably meet Saeed next down in Jeffrey Mountain. So just stick to your original timetable, and hopefully Steve will be here by 12, which is in your algebra lecture at 12. We'll all just shift around. You still go to the same places on your timetable. So what we're going to talk about in this hour is back to my material in the mathematics fundamental. We're going to do one more lecture on this short chapter at the end on groups, an introduction to groups. The group theory is explored in great detail in the third year unit. It's taught by me and Jan Bonnie. So it's a whole third year unit investigating group theory, looking at the structure and some of the main results that we have. And this short chapter at the end is just to give you an introduction to some of the basic concepts and see some of the notation, and just to get familiar with the set. So just a quick review of what we covered last week. Again, please make use of the lecture recordings if you weren't here, to catch up. But we met the definition of this basic kind of algebraic system called group. Fits into a kind of hierarchy of algebraic systems, go by the names of groups, rings, fields, algebras, so on. Lots of other associated kind of structures. So this is algebra. This is the study of the structure and the features and the possibilities for systems of number-like objects or transformation-like objects, and the way they combine together, and what the possible structures are. So specifically a group, we met the definition last time. A group was a pair consisting of a set and what's called a binary operation. So a binary operation, well, you already know you already know several examples of it. Important binary operations, are addition of numbers, multiplication of numbers, addition of matrices, multiplication of matrices, and very, very, very important, composition of functions. Those are all examples of binary operations. You have a set of elements of a certain kind, a set of a certain kind of numbers, a set of a certain kind of matrices, a set of a certain kind of functions. And this operation is a device or procedure for taking two of those and producing a third object of the same type. You take two numbers, you add them. You take two numbers, you multiply them. Take two functions, you compose them. These are all examples of binary operations. And if you have a set G and a binary operation here represented by the asterisk or the star, that pair forms a group if they satisfy these four properties. These are often called the group axioms, four group axioms, four group axioms. These are sensible, mathematically meaningful properties to have, and any system that kind of satisfies these properties is we regard as kind of being well behaved and mathematically meaningful. So the system is closed under the operation. A times B is always in G. The operation is associative. Triple products like that. Doesn't matter which way you evaluate the pairs. So A times the product of B and C on the left is the same as the product of A and B times C on the top. There's always the third axiom says that there's always a special element called the identity in the set. And that has the property that when you take the product of any other element A or E, the identity, and that it just returns the value A. And in partner with that property, we also have the existence of inverses. For every element in the set, for all A and G, there exists an inverse element with an A superscript minus 1. And that is the property that when you take the product of A and its inverse, it gives you back the identity element. Mentioned in chapter 3, mentioned in maximum 2. So what we did last time was we met this definition and we looked at some examples of We briefly talked about some of those early results there. Then we looked at several examples of groups using some very familiar number-like objects, integers, rationals, real numbers, and so on, under both addition and multiplication. And then I also, it's not in the notes, but we did it on the visualizer. We looked at an important non-number-like example, and that was all the symmetries of a regular triangle. That was the dihedral group D3. And that's the first one in a large family of groups. Symmetries of the square, symmetries of the pentagon, symmetries of the hexagon, and so on. Symmetries of an n-sided regular polygon that forms the dihedral group. Okay, so what we're going to be looking at today is another source of example, very important example of a group. So these are in permutations. So we'll just have a quick look at this definition, first of all, definition 5.15. So a permutation, by a permutation we mean, we mean a permutation on n objects, where n is some number, some positive integer, and a permutation on n objects is going to be a bijective function, a set of n objects to itself. Bijective function, remember that means one-to-one and onto, from a set of n objects to itself. Now, for convenience and convention, the usual set of labels we use for our n objects are the numbers 1, 2, 3, 4, 5, 10. Okay. But you just remember that we're just using those as a set of distinct labels. Equally well, you could label the n objects A, B, C, D, E, F, G. You have enough letters. And in the work that we do with permutations, we never really use any of the numerical properties of these labels. They're just a convenient set of distinct labels that we can take of our separate objects. Now, if you're studying statistics, you may well have come across the concept of permutations and combinations, some basic exercises in probability, the binomial coefficients, and several places you would have needed to count the number of permutations of a certain set of objects, or count the number of ways of choosing a certain subset from a certain larger set. So those kind of considerations can be important in basic probability. But here in this algebraic setting, we're interested in focusing on the individual permutations themselves, the individual functions. So let's look at just a couple of quick examples of permutations. So we'll take a couple of examples, two permutations of 5 objects. So I'm going to label my objects 1, 2, 3, 4, 5, and I want a bijection from this set to itself. So I'm just going to draw a mapping diagram of the elements of this set to themselves. So I'm going to call this permutation sigma, and this is the function that sends 1 to 2, 2 to 4, 3 up to 1, 4 to 3, and it's going to send 5 to 5. Okay. So this is a permutation sigma. Sigma is a function. Sigma of 1 is 2. Sigma of 2 is 4, and so on. Okay. Values are indicated there in the mapping from going from arguments to values. It's the same set, the set of these 5 objects. It's clearly bijective, it's clearly one-to-one and onto. You never have 2 different arguments going to the same value. Let's look at a second one. I'll label my second one as tau, Greek letter tau. And tau is going to send 1 to 1, 2 to 3, 3 to 2, 4 to 5, and 5 to 4. So tau is the second one. Tau 1 equals 1, tau 2 equals 3, tau 3 equals 2, and so on. Its arguments and values are as indicated there in the mapping diagram. So those are a couple of examples of individual permutations. Now, in order to form a group, remember, a group is a set of objects of interest, but really vitally important is the group operations. So our objects here, these individual permutations are functions from a set itself. So the natural operation that you can do with such functions is to compose, to run one function after another. So the operation I have here, composition of these functions. And of course, if you've got two permutations, there's two ways to compose them. You can do sigma after tau, compose it the other way around, tau after sigma. And of course, we should remember, composition of functions is inherently non-commutative. Doing operations one after the other is most of the time, almost all of the time, very sensitive to the order in which you do. So let's just have a look at these two compositions. So the natural one to do first, because it's kind of sitting in front of us, is to do tau after sigma. Tau after sigma, we could draw the mapping diagram for that. The mapping diagram for tau after sigma is just kind of running, so applying sigma first and then tau. So you're just kind of running all the arrows together. So where does 1 go? Well, 1 goes to an intermediate value of 2, but then it goes on to 3. So in total, 1 goes to 3. 2 goes to 4 under sigma, but under tau, applied second, that 4 gets sent on to 5. So in total, 2 goes to 5. 3 goes to 1 under sigma, but then tau sends 1 to 1. So 3 in total, 3 goes to 1. 4 goes to 3, goes to 2. And 5 goes to 5, goes to 2. So that's the mapping diagram for tau after sigma. And out of interest, it's probably going to be different. We could look at sigma after tau the other way. Draw the mapping diagram for this. So this time we have to compose them the other way. So under tau, 1 goes to 1. So 1 is the intermediate value. And then sigma is applied to this intermediate value of 1. Sigma sends 1 to 2. So in total, 1 goes to 2 when you apply tau after sigma to 2. What happens to 2? Well, when you apply tau to 2, it goes to 3. But then sigma is applied to this intermediate result. Sigma sends 3 to 1. So in total, 2 goes up to 1. So already you can see it's different permutation to tau after sigma. So you can keep filling it in. 3 goes to 2, and 2 goes to 4. So 3 goes to 4. 4 goes to 5, and 5 goes to 5. So 4 goes to 5. So it better be that 5 goes to 3, 5 goes to 4, 4 goes to 2. Notice typical feature that tau after sigma is a different function, different permutation than sigma after tau. Sometimes pairs of functions can commute. Typically, they won't. Everybody okay with just that basic? I mean, we talked about function composition in chapter 3. Everybody okay with this basic idea? So this is just looking at 5 objects. You can play this game. You can look at these permutations on any number. So the group that's in this picture is there in definition 5.16. So it's what we call the symmetric group. It's labeled Sn. That's the group of all the permutations on n objects under the operation of composition. It's clear that if you have 2 permutations on 5 objects, say, when you compose them, you always get again an object at the same time. You get again a permutation on 5 objects. Composition of permutations will be an operation that we can perform. There's always the identity transformation. The identity transformation just sends every object to itself. Pose something with that identity, it won't affect that. It will just give you the same permutation that you're composing. And there's an easy inverse. It's easy to see what the inverses are. I mean, what's the inverse of sigma? The inverse of sigma is just if you just reverse the direction on all the arrows. Here, you'll see the inverses. The inverse of sigma would send 5 to 5, 4 to 2, 3 to 4, 2 to 1, and then to 2. Just invert the translation. Now, before we go a little bit further, because this might seem a little artificial, let me just briefly indicate to you the reason why these groups are of interest. Where are the lecture recordings? If I go to last week's lecture, just bring it up the. I need to listen to it. If I go to last week's lecture and just bring up the notes on it. Let's look at the Cayley table that we drew. This was the Cayley table for the dihedral group D3. Okay, so there we were looking at how these various reflections and rotations combine. But what you notice there is just what you're seeing in front of you in the Cayley table. If you look at each row, what you can see there is in each row, you have got a permutation of the original set of elements. Yeah, the set of elements in D3 is E, R, R squared, S1, S2, S3. Okay. The identity, the two non-identity rotations, and the three reflections. In each row of the Cayley table, is naturally associated with each of the elements. In each row, you see a permutation of the set of elements. You see each of the 6 elements once and only once in each row. So what that means is there's a natural way that you can think of this group as being a subgroup of S6. Because you can associate each element of D3 permutation of 6 objects. And that connection is very important. It's an example of what's called Cayley's theorem. Cayley's theorem says every finite group is essentially the same as a certain subgroup formed by a selection of permutations. Permutations are these rows in the Cayley table. You look at the other groups we formed. We looked at the modular arithmetic groups. This was Z6 plus and the multiplicative group Z9. The multiplicative group Z9. In each row of the table, you're again looking at in each row a permutation of the original set of elements. So that's why this symmetric group Sn is of such interest. It essentially can do the job of representing any finite group. So this looks kind of specialized and particular, but in a sense, it's quite universal. Yes, question.
Does that mean that we can use results from permutations on the other group?
Yeah. So it essentially means is if you could completely understand permutation groups, you've essentially understood every finite group. Okay. Now that at first hearing that sounds like a kind of a simplification method. That the world of groups isn't that complicated because you can represent it just as permutation. But that's kind of the wrong way to think about it. It's not so much a simplifying result. Rather, it's saying this one example of a family of groups which you thought was maybe contained and simple enough. It's not. It's as complicated as the whole universe of groups. So it's really a result that tells you just how complicated and rich the structure of permutation groups is. But it does give you a way to represent, in principle, every group. And it gives you a way, these permutations can be easily encoded in computer language, computer programming language. So it gives you an inroad into doing computations. So the third year group theory unit, we use this a lot. Study groups via their representations as permutations. Okay. So now, it's a bit of a chore all the time to keep drawing these mapping diagrams. So we need a bit better, more compact notation. So there's two main types of notation that we can use with permutations. Oh, sorry. Before we get on to notation, first of all, I just want to talk about theorem 5.6. The size of the group Sn. So when we say the order of a group, we just mean the count of the number of elements in it. So theorem 5.6 says that the size of Sn is n factorial. And that's quite easy to prove. Okay? So if you think about, consider forming a mapping diagram. Consider forming a mapping diagram of a permutation. You have the elements 1 to n, and you've got to start drawing arrows across the diagram. So for your first arrow, it's going to come out of 1. Where is the arrow going to go? Well, there's n different locations where the arrow can go. The arrow from 1 will go somewhere down here, but you've got n choices for the first arrow. Okay, then you've got to draw an arrow coming out of 2. That's going to go somewhere, but for the second arrow, how many elements might it go to? N minus 1, yeah. Because we've already assigned one of the elements as a value for 1. And this permutation has to be injected, has to be a one-to-one function. So we're not allowed to send 2 to the same element that 1 got sent. You've got n minus 1 choices. So after drawing your first arrow, which you've got n choices for, you've got n minus 1 choices for your second arrow. The 2 will get sent. And then you can see what's kind of happening. Then you've got to send 3 somewhere. So for the third arrow, how many choices you got to draw your third arrow? Just n minus 2 elements. And so on. How many choices when you get to the nth arrow? Yeah, you don't really have any choice. There's just one, there'll only be one remaining element here which hasn't been assigned, and that's going to have to be the value for n. One choice. No choice. So how many different possible mapping diagrams are there? Well, you just looked at the total number of choices. The total number of choices, well, you've got n choices. For each of those, you could make n minus 1 separate choices for the second. Having chosen the first 2, you then got n minus 2 choices for the third, and so on. So the total number of choices here you get by multiplying together these options. Total number of mapping diagrams, which is the same as the number of permutations, is n by n minus 1 by n minus 2, all the way down to 1. So in other words, it's n factorial. So relatively straightforward to say how big the symmetric group Sn, size n factorial. N factorial grows very fast. Okay? By the time you get to S10, it's 10 factorial, which is a pretty large number. Okay? And it only continues to get very fast, almost exponential growth. So it's easy enough to say how big the symmetric group is. So different types of notation. The mapping diagram is quite good. Visualizes in a nice way what's going on in permutation, but it's a bit awkward to draw on the page. And so you can compactify it a little bit into what's called a two-line notation. So the two-line notation is essentially the same as a mapping diagram, but you just simply arrange the arguments in the first line and the values in the second. Okay. So sticking with our examples. So the above examples, sigma tau, in two-line notation, sigma would be, so there's 5 arguments, 1, 2, 3, 4, 5, and you just simply put the associated value underneath.
Sigma of 1 is 2, sigma of 2 is 4, sigma of 3 is 1, 4 is 3, 5 is 5. Tau would be 1 goes to 1, 2 goes to 3, 2 goes to 2, 4 goes to 5.
So it essentially just is the mapping diagram, just without the arrows and just written as a matrix, two-row matrix.
So this is essentially, this is the essential information. This is the essential info from the mapping diagram.
So it's no more useful really than a mapping diagram. But there's a much better, more insightful kind of notation we can use. So it's better. It's more insight in it, more insightful. Over grammar. Second, more insightful, meaningful notation is the cycle notation. This is a much cleverer way of representing permutations. It tells you a lot about the inherent structure in the permutation. Now, what do I mean by the structure? I mean, we've seen our mapping diagrams. You've got a lot of arrows going across. You can see everything that's going on, but there might be a lot of structure to the permutation that isn't so immediately apparent from the mapping diagram. Okay. So we'll take a nice biggish permutation on 8 objects from U. There's a bit more going on here. You got 8 objects. So we'll look at this example. That's 718, 35624. Okay, so there's its 2-line notation. Essentially the mapping diagram. What better way could there be to think about it? Well, there is a much better way. Let's draw a mapping diagram now, but let's just scatter our elements around the page. Remember when I said at the start that these numbers 1 to n, they're just being used as a convenient set of labels for the object. We're never using the fact that 2 is bigger than 1 or 8 is divisible by 4. They're just purely being used as distinct labels. Equally well, we could call them A, B, C, D, F. Now we're going to draw a second arrow diagram, but this time just rather than going from one copy of the labels to a separate copy, we're going to just use the same copy of the labels. And this starts to show some of the structure. So let's draw the arrows on. So 1 goes to 7. So you draw an arrow from 1 to 7. I'm not so much interested in 2 right now. Rather, I'm interested in 7. So let's see where 7 goes. 7 goes to 2. Now I'm interested in 2. Where does 2 go? 2 goes back to 1. So what's revealed to us when we do it this way is that we've got that thing we call a 3 cycle. Cycle of 3 elements. There are 3 elements that are in a club together. Each one gets sent to the next one by the action of U. I'll pick up a different color now. So that was green. Let's go for something else. 4. What happens to 4? 4 goes to 3. Where does 3 go? 3 goes to 8. 8 goes to 4. Another cycle. There's a second 3 cycle. What happens to 5? 5 goes to itself, and 6 goes to itself. So this is what I mean by saying the structure of the permutation. We can now see what we call the cycle structure of the permutation. So we see that mu consists of 2 3 cycles and 2 1 cycles, trivial cycles. So that's a much more interesting way to look at the permutation, and we've got a cycle notation that reflects that. Okay. So the 3 cycles can be written, well, we won't do a 2-line notation, we'll just do one set of symbols. We'll just simply list these symbols in the order that they occur. So the symbols in the green cycle are 7, 2, 1. The symbols in the red cycle are 4, 3, 8. Yes, question.
Does it matter what order the numbers are in?
No. So is there a first element in the green cycle? No, there isn't the notion of a beginning and end. It's just a cycle. So you could write it. So you could write it anyway, as long as you respect the cyclic order that they occur. Yeah. So equally well, I could write this. Yeah, you're right. It's 1, 7, 2, or what's the other way? 2, 1, 7. Those are all equivalent representations of that 3 cycle. You wouldn't represent it as 2, 7, 1, because that's not the order. You simply list the order, reading from left to right, that they occur in the cycle. So equally well, your 4, 3, 8 could be written in any of the other ways. And the 2, 1 cycles, well, 5, 6, 7. Trivial cycles we often call. So we can write mu now and we can express mu as, you see, these cycles are representations of component permutations, smaller permutations. So 7, 2, 1 is a cycle. It's a permutation of those 3 objects. So we can compose these like this. So we can do 7, 2, 1 after 4, 3, 8. And that's after the trivial cycle 5 and the trivial cycle 6. But now let's look at definition 5.18, which is the full definition of a cycle. So a cycle, definition 5.18, a cycle is just a 1-line list of elements, and it represents the permutation that cyclically permutes those elements in the order. So this example up here, sigma 1, 3, 5, 2, 4, that's the permutation that sends 1 to 3, 3 to 5, 5 to 2, 2 to 4, and the last one, 4, is sent back to the first element. Now, we understand by convention that sigma, we can also regard sigma as acting on other elements, which are not mentioned in the list. Any other element that isn't listed in the cycle notation for sigma, we understand sigma to act as fixing those elements. So if we ask what that sigma does to 6, well, it sends 6 to 6. To do to 7, it sends 7 to 7. To do to 8, it sends 8 to 8. Any object that isn't mentioned in the list of objects in the cycle, we'll take it as understood that that cycle is considered to act on those elements as well, but it acts on them by fixing them. So when we write mu like this, we're actually writing mu. This is a composition of permutations. So it's 7, 2, 1, after 4, 3, 8, after 5, after 6. These cycles, you can see a definition there, 5.19, these cycles are what we call disjoint. Disjoint cycles are cycles that operate on separate sets of elements. Okay? So the green cycle is disjoint from the red cycle. They don't interfere with each other. Okay? Green cycle is doing its own thing, the red cycle is doing its own thing. They don't interact. I know the lines cross, but that's just the lines crossing. The set of objects in the cycle are completely different. So that means that while this is a composition, remember before when I was showing you the first pair of examples of sigma and tau, we emphasized the point that sigma after tau was expected to be different to tau after sigma. Composition of functions is expected to be non-commutative. Typically matters what order you do operations. Okay? Just in general, in life, you got to do things in the right order, otherwise the effects will be different. But when we're working with disjoint cycles, it is always commutative. Okay? So we note that disjoint cycles always commute. That means it doesn't matter in what order you compose disjoint cycles. Because they act in completely separate elements, it doesn't matter which one you do first and second. Because the actions of one does not interfere with what the other one's going to do. So equally well, we could write mu as 438, 5, then do the cycle 721, and then do the cycle 6. And because of the convention that if a symbol isn't mentioned, it's assumed that the cycle acts by fixing that element. By convention, that allows us to omit or drop the trivial cycles. Cycle convention. Full part of definition 518. The cycle convention allows us to drop mention of the trivial cycles. They're still there. If we regard mu as an element of S8, permutation on 8 objects, we can see its cycle notation there, 438 after 721. Still understand, because 5 and 6 are absent, then this mu is fixing those elements. U sends 5 to 5, and sends 6 to 6. So this kind of notation, this is called the cycle, full cycle notation. And the way of representing permutations as products of disjoint cycles. And this is very useful, okay? So this disjoint cycle notation is the preferred notation, as it conveys most information about the structure, about what's really going on with permutation. It conveys so much information. So let's do a little exercise. What we'd like to be able to do is to become quite practiced with this. Okay, so set ourselves a little exercise. For this exercise, we're going to obtain the disjoint cycle representation of this new permutation. We're going to call lambda. The lambda is a composition. Now it looks like it's already in the required form. Looks like it's already in the required form. It's already a composition of cycles. Cycle 1, 3, after the cycle 2, 4, 5, after the cycle 2, 3, 5. But what we notice is that they are not disjoint. Those cycles operate, they do interfere with each other. 2 and 3 are mentioned in the cycle, the first one that gets applied, the one on the right. 2 and 5 are also in the middle one, and 3 is also in the left. So they're certainly not disjoint.
These cycles are not disjoint. So we're not yet seeing the kind of fundamental form of that permutation like we saw for the mu earlier on. Okay. But we can obtain it very easily. Now you could either go back to this way of doing it, and this is a good way to do it at first to get insight into it. You could scatter the elements across the page and draw in the arrows in different colors. Follow each cycle around and color it differently, and then you'll see it before your eyes. Okay. But you know, you can do that in just using the compact notation. So this is going to be, we'll accept this as an element of S5, the whole lambda as an element of S5. So it's fairly easy to actually just essentially do that job of drawing in the different colored cycles, but just do it completely within the cycle notation. Because one of those colored cycle of arrows has got to feature the number 5. So one of the cycles will have a 5. Remember, it doesn't matter where you start because there is no start or end to any of these cycles. They're in a closed set of elements. So let's just pick 5 as a starting point because why not? Okay. So what comes after 5 in this cycle? The disjoint cycle. So we have to work out where 5 gets sent to by lambda. Okay. So what is lambda 5? Lambda of 5 is the element that's going to go in this position here. So what is it? 4. Okay. So how did you work out 4?
5 goes to 2, and 2 goes to 4.
Yeah. And what happens to the 2? Well, what happens to the 4? Oh, yeah. So what you did there was this cycle, this 3 cycle is the first one that gets applied. The sigma is a composition of these 3. This one first, then this one, then this one. So what does this one do to 5? This one sends 5 to 2. Remember, the last one in the cycle gets sent back to the first one. So this one sends 5 to 2. So 2 is the intermediate value, which then this permutation operates. This permutation operates on the intermediate value of 2 by sending it to 4. So 4 is like your second intermediate value. The composition isn't over yet. The composition has to apply this third cycle, 2 cycle, to 4. Well, what does this do to 4? Well, this one doesn't mention 4. Remember, the convention is if the element isn't mentioned by a cycle, it leaves that element fixed. So this element fixes 4. So 4 is the final value that comes out, being the value of lambda applied to 5. So this cycle, whatever it is, must have a 4 following 5. But what we've done there is essentially drawn the arrow from 5 to 4. Let's draw the next arrow. What goes beside 4? Well, it's going to be lambda of 4. So what is lambda of 4? Let's do the same thing. The first cycle fixes 4. 4 isn't mentioned. So 4 goes to 4 under this first cycle. Then 4 goes to 5. 5 is the intermediate value. That's passed on, and the cycle 1, 3 acts on 5. Intermediate value. And of course, it fixes 5 because 5 isn't mentioned. So overall, 4 gets sent to 5. So if I wasn't being careful, I'd be tempted to write down 5 beside 4 here. Of course, I don't do that. Because the cycle, the convention of the cycle notation is if 4 gets sent to 5, well, that's what you're seeing there is the end of the cycle. So 5 and 4 are just in this short cycle of length 2. 5 goes to 4, 4 goes to 5. So we've already discovered there that within the structure of lambda is this 2 cycle 4, 5. And that's going to sit there and be composed with another disjoint cycle. So one of them's got to mention 3. Okay. What happens to 3? Do the permutate. The first one sends 3 to 5. The second one sends 5 to 2. The third one fixes 2. So in total, 3 gets sent to 2. And what happens to 2? 2 goes to 3. 3 goes to 3, fixed, then 3 goes to 1. So in total 2 goes to 1. Probably the end of it, because we mentioned the 5 symbols, but just for consistency, just check what happens to 1. 1 is left fixed, 1 is left fixed, and 1 goes to 3. So 1 gets sent back to 3. So actually that's the closure. So what we've just discovered there really is we've just done a compact form of discovering the disjoint cycles as these two cycles. So the structure of this lambda is a 3 cycle and a 2 cycle. Now there's multiple different ways of writing it. You can choose 5 as the first element in this 2 cycle. You can choose to write it 4 or 5 instead. You could have chosen 3 as the first one of these. So there are multiple equivalent ways of writing these. And of course, you don't have to have it the 2 cycle after the 3 cycle. Equally well, you can do it 3 cycle after the 2 cycle. But that doesn't matter because they don't. It doesn't matter which one. Like if you have to apply lambda, you have to click, to send every element onto the next one. It doesn't matter if you click on the 2 cycle before clicking on the 3 cycle because they don't interact. So this is what we call. So this is a look at the 2 main types of notation for working with these permutations. 2-line notation, which is essentially equivalent to our original mapping diagrams. Very good, early intuitive way to think about functions. But then, because these are functions from a set to itself, it makes sense to just focus on the one set of elements. And of course, then we discover that you naturally discover this fundamental cycle structure of permutations. And this is encoded in this cycle notation. Okay, so you will find a few more results talked about there. So I'd encourage you to read through. You should definitely read through the rest of that chapter. And in your tutorials this week, you can do examples of the end of chapter exercises. And in my lecture, I'll be seeing you twice next week for 2 lectures. So I'm going to look at some of the past papers and do some example exam questions with you. And because it's fresh in our minds, I'll probably start with some of the group theory, so some of the questions that featured some of these group elements from last year's paper, and then work my way through some other questions. Okay, so thanks for your attention, guys, and I'll see you for a couple of lectures next week.